In this video, we're going to talk about enols and enolates. We'll start off by talking about the difference between the enol and enolates. Then we'll look at some acid-base considerations, and then we'll actually look at the difference between kinetic and thermodynamic enolates. So for starters, let's look at what the difference between an enol and an enolate is. If we take a ketone, like the cyclopentanone here, and we treat this under mildly acidic or basic conditions, we can form an enol. Now we've seen this before in this keto-enol tautomerization. And in most cases, this is going to favor the carbonyl side. So we're only going to be forming a small amount of this enol in solution. However, sometimes that can be enough to do our chemistry. If we change our structure a little bit, where now we have two different carbonyls, then we actually see a higher percentage of the enol that forms. So this is going to be much more prevalent in solution than this particular enol is going to be. If we take the same type of ketone and treat this under basic conditions, we can deprotonate one of the hydrogens here to form what we call an enolate. The chemistry of the enolate and enols is going to be similar, but it is going to be distinctly different. In the next section, we'll look at the acid-base considerations and determining which side of the equilibrium we're going to favor in the case of the enolates. So here we have two different acid-base reactions that we can look at. I'm using the same cyclopentanone, but I'm going to look at the difference between using methoxide as a base and this diisopropyl amide. So this is from LDA, lithium diisopropyl amide, and then this would be from sodium methoxide. Now in both of these cases, we can pull off one of these alpha protons to form an enolate. In the first example, we would generate methanol. In the second example, again, we pull off that alpha proton, form that same enolate. But now we're generating an amine. And if we look at these, we can compare the pKa's of the different hydrogens to get an idea of which side of this equilibrium we're going to favor. So if we look at our cyclopentanone, these alpha hydrogens have a pKa of about 26. And if we look at our first example, methanol has a pKa of about 16. The amine has a pKa of about 36. So if you remember back to our acid-base chemistry, we always favor the side of the weaker acid. So the higher our pKa number, the weaker that acid is going to be. So in our first expression, this hydrogen is much less acidic than methanol, 10 orders of magnitude less acidic. So if we looked at this equilibrium, it's going to heavily favor the starting materials in this case. We're not going to see a whole lot of that enolate generated in solution. However, in the second example, we have the opposite case. Now this amine is 10 times less acidic as the alpha hydrogen in our cyclopentanone. That means that the product side is going to be heavily favored in that example. If we look at a third example, here I have two carbonyls. I'm going to use our weaker base of these two. The enolate that we form in this case is stabilized by both of these carbonyls that are present. And again, we're generating methanol. If I compare the pKa's in this case, our pKa of methanol was 16. Our pKa of our starting diketone is about 9. So in this case, this is the stronger acid. So having that second carbonyl allows us to form that enolate in that case. So this gives us an idea of how the strength of the base affects the relative equilibrium of that pKa. In the next example, we're going to look at the difference between a thermodynamic and a kinetic enolate. So now let's look at a new example. I've added a methyl group to my cyclopentanone, and we're going to see that there's two different enolates that we can form. If we pull off this hydrogen, We can form an enolate on this side of my structure. If I pull off this hydrogen, I can form an enolate on the other side of my structure. Now these look very similar, but there are some differences. The hydrogen here is actually more accessible. It's easier for us to access that hydrogen, but it leads to a less substituted alkene. This hydrogen is not as accessible. However, the enolate that we form is the more substituted alkene. This one where we have the more substituted alkene is more stable. This is our thermodynamic product. In this case, where we're removing the more accessible hydrogen, this is going to be our kinetic product. The conditions that we're going to use to isolate these two things or form these two things is also going to be very different. Typically, under thermodynamic conditions, we can use heat. We can use the same type of base, such as LDA, but we don't want to use a full equivalent of that LDA. That allows us to form some of this enolate, but we have more of that stuff that's there. So actually, the first enolate that we would form is this enolate. Kinetically, this is going to be the fastest enolate for us to form. If we use more than one equivalent, all of this is going to be funneled into this less substituted enolate. That's why we have just over one equivalent of our LDA. The other thing that we're typically going to see is that this is run at very cold temperatures. So most people associate that cold temperature with our kinetic conditions. However, in our thermodynamic case, we actually form this initially, but if we don't have the full equivalent, some of this enolate is now going to react with the unreacted stuff at the more substituted position and kind of funnel it to the more thermodynamic enolate. So both of these form this enolate first, but if we don't have enough of that base around, it all funnels to that more thermodynamically stable base, or stable enolate. Typically, these are run at 0 degrees or higher temperatures. That's one way that we can identify the difference between the thermodynamic and kinetic enolates. Hopefully you find this information useful as we start to study the chemistry of these alpha carbons.